Great. Hello, everybody. My name is Alessia, and I am the lead lecturer here at Pearl Street Studio. And welcome to our introductory lecture on geothermal. So, geothermal is one of the many energy resources that's used around the world for generating electricity. So, the goal of this lecture is to help people understand what exactly a geothermal resource is, how a geothermal resource can be used to generate electricity, and then discuss some of the considerations around using it as an energy resource. Now, before I dive in, I did want to note that this is lecture 4 in this unit. This is part of a broader course that we are building called Introduction to the Electricity Industry. If you haven't already, we highly recommend that you go back and watch our lectures on coal, crude oil, and natural gas, as this lecture references some of the material that we went over in those lectures. If you haven't watched them, we will add a link in the notes to the YouTube video for our previous lectures, but you can also find these videos at our website at pearlstreetstudio.org. All right, with that, let's dive in. So, what is geothermal energy? Geothermal energy is a thermal energy that originates from deep within the earth and can be harnessed to generate electricity or provide heating. So if we think back to when we took geology, whenever you took it at some point, whenever it was covered in your education, you'll remember similar images to this one here, as there's an earth, and here I've taken a little chunk out of the earth, and this sliver here is supposed to represent a little chunk that's taken out here. And there are four main layers of the earth. There is the crust, which is where we all are at. We are living here on the surface of the earth. And then underneath the crust is the mantle, which is filled with a bunch of magmas. And then there is the outer core and the inner core, which is it's a mix of like liquefied and solid metals and like crystals and diamonds and stuff like that that's located all the way down here. And so what geothermal energy is, it's the heat that's coming from the mantle and it is permeating up through the crust here. So that's what it is, most simply. Now, what can geothermal resources be used for? So there are two main applications. There is building heating and cooling, and there is electricity generation. So building heating and cooling here, there is a technology, this little loop thing that I've drawn here, that's called a geothermal heat pump, also known as a ground source heat pump. And it's a technology that uses the relatively constant temperature underground to heat or cool a building. So underground, usually about 1 to 2 meters underground, the temperature remains at about 15 degrees Celsius. And this is from the heat that's rising from the mantle. This temperature, here is typically about 15 degrees Celsius. So how, in the heating application, the building heating application for a geothermal heat pump, let's say it's 0 degrees Celsius out. So it's winter time, it's pretty cold. So what happens is a cold liquid is cycled through and then goes underground, and this liquid is colder than this underground resource, so it picks up some of the heat from the rock or the dirt underground, is cycled back up, it releases some of that heat into the building, and then cycles back around. And then it's basically just flipped in the cooling scenario. Let's say it's a hot summer day, it's 28 degrees Celsius, and what happens is a liquid is cycled through a building, it absorbs some of the heat from that building, it is cycled underground where it is warmer than the underground temperature, so it exchanges some of that heat, it releases some of that heat to this underground area of rocks and dirt. It cools down, then comes back up to the building, picks up some of that heat, and is just cycled through. So this is one of the examples of a geothermal resource. But the one that we're going to be talking about in this lecture is its applications, whoops, my screen glitched a little bit, for generating electricity. So a geothermal power plant generates electricity by using heat that's deep within the crust of the earth, heat that is permeating up from the mantle. And so in this system, a well is drilled down or into a region that has hot rocks, and it's typically drilled at a depth of about 1 to 3 kilometers deep with current technology, but there's some advancements in drilling technology that's allowing us to drill even deeper. But for now, let's just say about 1 to 3 kilometers deep. And then what happens is that sometimes water can be found in these regions. If not, water can be artificially piped down. That water picks up that heat, is generally turned to steam or a mix of water and steam, is then pumped to the surface. That steam is then used to spin a turbine, and then once it cools down, it's pumped back underground to iterate through this cycle. And the way that it generates electricity is very, very similar to how coal-fired power plants and natural gas power plants generate electricity. So here, if we look at this diagram, it's the same thing. So we have that steam, and that steam is being put through a steam turbine. My handwriting's a little messy. Turbine. And that steam rotates a turbine, which then takes that rotational kinetic energy. It's then attached to a generator here. And that generator takes that rotational kinetic energy and turns it into electrical energy. And then through these power lines here, it transfers that energy to the electric grid. To then be distributed to consumers like us. So that's how it works on a high level. But there are actually 3 different types of geothermal power plants that I'm going to discuss. So the first one is a dry steam power plant. And a dry steam geothermal power plant uses some underground geothermal reservoir that has water in it to generate electricity. And the temperatures of these underground rocks here is typically above 235 degrees Celsius. So it's very, very hot down here. And it's, as I described before, water's pumped down, it is then cycled through, it picks up that heat, it's delivered up here as steam to go through a turbine. So the same scenario that I showed before. Now, there are not a lot of areas around the world where you can drill 1 to 3 kilometers down and the temperature is as high as 235 degrees Celsius. But some of the 2 of the locations around the world that do have dry steam geothermal power plants are the geysers in Northern California, located in the United States, and then also in Lardello, Italy. Okay, the second type of geothermal power plant is a flash steam power plant. And in a flash steam power plant, it of course generates electricity using hot geothermal water, but the temperatures are typically around 182 degrees Celsius. And here, again, a well is drilled down, that water is then permeates through the rock, picks up some of that heat, and then is pumped to the surface as a mix of water and steam. Now, here I mentioned that the temperature is typically at 182 degrees Celsius. So let me draw this here. So here it's typically above 182 degrees Celsius. And now if we remember our very, very basic chemistry, we know that water, at least at the surface, on the surface of the crust, boils at 100 degrees Celsius. So why is not all of this just steam? And this has to do with pressure. So up here at the surface, the pressure that we are under up here is at 1 atm. So an atm is an atmosphere, and we are at 1 atmosphere of pressure up here. Oh, hold up, I deleted part of my flash steam. Let me redraw this here. So here we go. I deleted part of my flash steam plant. Okay, let me get back to this. So here it's 182 degrees Celsius or above. Up here we're at 1 atmosphere. And at 1 atmosphere, the boiling point of water is 100 degrees Celsius. But down here, when we're at around 3 kilometers underground, the pressure that this is under from all the rocks and dirt that are above it is at about 800 atmospheres. So it's at much higher pressure underground. So water that is located underground, despite being 182 degrees Celsius, is still in a liquid format. But then as the water is pumped up to what is called a flash tank. A flash tank here. In the flash tank, it goes, or from the bottom, which is at about 800 atmosphere, to the flash tank, it's at about 1 to 3 atmospheres. So it's at a much lower pressure when it gets to the flash tank here. And so when it arrives to the top, it is a mix of steam and water. Now, here, rather than converting, even though it's at this very high temperature and it's brought near the surface, rather than converting entirely to steam, actually only a portion of this water flashes into steam. So some of it, even when it gets up here, is steam and water. Now the reason why it doesn't all turn to steam has to do with a concept called the latent heat of vaporization. But I'm going to gloss over that concept for this lecture, and I'll explain how that works in more scientific detail in a future course. But for now, let's just accept the fact that it comes up to the surface. Part of it is converted to steam, which goes through this steam turbine here, and then part of it stays as water and then is just re-injected back into the well. Okay, so that's how a flash steam system works. Let's go. The third system, or the third type of power plant, is called a binary power plant. And in a binary power plant, the main difference is that the temperature is at around 100 degrees Celsius. So it's still warm, but it's not hot enough to typically produce steam. And so what happens is that water is pumped underground. It is then brought up it goes through, it collects some heat, and then it is then pumped to the surface. But the hot geothermal water is then passed through what we call a heat exchanger here. So here I already have it labeled here, a heat exchanger. And so what happens here, instead of water turning to steam, to spin a turbine, the geothermal water transfers its heat to a secondary fluid that has a much lower boiling point than water. So what happens in this heat exchanger, some of this geothermal water gives its heat to this secondary fluid. This secondary fluid then vaporizes into a high pressure gas, and then it flows through the turbine, causing it to spin. Then on the other side, it is cooled and condensed back into a liquid where it's passed back through that heat exchanger. So it goes through that loop. And so the geothermal water here is then just cycled around here, coming down here, picking up some heat, transferring that heat to the secondary fluid, and then being sent back down to go collect more heat. So those are the 3 different types of geothermal power plants. Now I'm going to talk about the conditions in which these power plants are built. Talk a little bit more about like the geological conditions. So there are these terms that you might have heard associated with geothermal, called hydrothermal and enhanced geothermal systems. And a hydrothermal system, or maybe I should add a natural hydrothermal system, in order to build out a geothermal power plant, has to have 3 requirements. There needs to be hot rocks that are at a certain temperature. There needs to be water that naturally exists already underground, and then the rocks have to be porous enough to allow the water to flow through the rocks and pick up that heat. But the thing is that there are not that limits, from a geological standpoint, that limits where geothermal power plants can be built out across the world. So there has been this new advancement in technology called enhanced geothermal systems. And so this enhanced geothermal systems are able to find an area that has hot rocks, but doesn't have these two other requirements of a natural water reservoir and permeable rocks, and it's able to create that kind of geological environment. And so how EGS works, enhanced geothermal systems, for shorthand EGS. How it works is that first a geologist locates where there are some hot rocks that are located underground. Then in the second step, some engineers use fracking technology, the same type of technology that's used for fracking for natural gas and crude oil, drills down into this layer of hot rocks. They drill this well. And then what happens is once they've drilled the well, they send a very high pressure fluid down into this well, which cracks the rock here. And so this is pretty much exactly the same process as fracking. And so then after creating these fractures in the rock, so it creates this artificial, it breaks up the rock, allowing water to permeate through this rock. And then what happens is that water is then sent down from the first well, from one well. That water is then able to permeate through and pick up the heat from these rocks that have been broken up. And then a well that's a little further away will take this hot water or steam and pump it up at another location. So in effect, EGS creates an artificial hydrothermal reservoir where one did not naturally exist. So the EGS technology is allowing geothermal plants to be built out in many more regions across the world where natural hydrothermal capacity doesn't exist. Okay, so now on to the characteristics of a geothermal power plant. So geothermal power plants are considered dispatchable resources because operators can control the flow of hot water or steam being pumped from the geothermal well. But geothermal facilities are typically operated at a relatively constant output in order to preserve a constant temperature and pressure underground here. Because if water is pumped through this system too fast, it can actually temporarily decrease the temperature of these rocks down here, which is destabilizes the system. Okay. For the fuel supply chain and the fuel storage, because there's no fuel that's needed for this system, there is no fuel supply chain and there is no fuel storage, which is pretty great. That cuts out a major part of running these systems. Okay, on to capital costs. So these numbers here are in US dollars from 2024. And here I am only going to talk about the capital costs of building out hydrothermal flash steam plants and hydrothermal binary plants. And this is because there are not a lot of regions around the world that are able to build out direct steam power plants because it requires that very, very high temperature. And then enhanced geothermal systems, the technology is still in the process of being built out commercially, so there isn't as much data on the capital costs of building out systems with enhanced geothermal technology. So, just to remind you guys, a hydrothermal flash power plant has hot rocks that are typically above 182 degrees Celsius, and it's in a region that has naturally permeable rocks and a natural underground reservoir. And here, for a system that drills about 2.5 kilometers underground, the typical cost is $4.8 million per megawatt. And why I've included the depth is because it's actually quite expensive to drill. So the further a power plant has to drill down, the more expensive it's going to be. So that's why I'm including that here. Now, hydrothermal power plants are typically the size of about 40 megawatts, so this means that the total cost for a system is at about $192 million to build out one of these power plants. And then on the other hand, a hydrothermal binary system, when drilling about 1.5 kilometers down, it costs about $6.3 million per megawatt. And this is because if we go back to these diagrams here, if we compare these two systems, binary systems are a little bit more complicated than flash steam systems. There is this whole separate loop with a secondary fluid in a binary system, whereas in a flash steam system, there is this flash tank, but the working fluid here is just the same water that's being pumped in a circle. So that's why binary is a little bit more expensive, or not a little bit, a decent amount more expensive. And so the typical size of a hydrothermal binary plant is about 30 megawatts. So the typical cost to build out one of these plants is about $189 million. And this data is coming from the National Renewable Energy Laboratory in the United States, also known as the National Lab of the Rockies. And this data is from their 2024 Annual Technology Baseline Report. Okay. Then for operational costs, I was having a bit of a hard time finding the data for the operational costs of geothermal power plants. I was able to get this from a website called the Whole Building Design Guide, but this number didn't come from the same report as this data, so in the next version of this lecture, I'm gonna dive a little deeper into finding this number, but what I was able to find is that the cost is about $10 to $30 per megawatt hour, which roughly makes sense. If you remember, the cost of natural gas was about ranged, I think, from $25 per megawatt hour to $45 or $35 per megawatt hour. And so here you can see the operational costs of geothermal are cheaper than natural gas. And this is because there's no fuel that is needed for this system. So that takes out a chunk of the operational costs. All right, now for air pollution and greenhouse gas emissions. So dry steam and flash steam geothermal power plants release small amounts of naturally occurring gases from the underground reservoirs. And for air pollutants, this includes hydrogen sulfide and mercury. And then for greenhouse gases, it includes carbon dioxide and methane. However, I do want to emphasize that these emissions are much lower than those produced by coal, crude oil, and natural gas fired power plants. Then, but for binary plants, they operate as a closed loop system, so that water that's going through a binary system, there is no opening or there is no exposure to the atmosphere. So any of these pollutants that come up in the water in a binary system are just piped right back down underground. So they have no air pollutants or greenhouse gas emissions associated with binary plants. Okay, now role on the electric grid. So geothermal power plants are used as a baseload generation resource because they can produce electricity continuously, independent of any weather conditions or the time of day. And although geothermal power plants are considered dispatchable because operators can control how much water is being pumped into the system, water and or steam is being pumped into the system, they are typically operated at a constant output of electricity in order to maintain the temperature and the pressure of the underground reservoir. Because if too much water, as I mentioned before, if water is cycled too quickly through the system, it can actually decrease the temperature, or temporarily decrease the temperature of the reservoir underground. Okay, on to the last section. So the geopolitical considerations of geothermal. So, because geothermal systems don't require any fuel inputs, unlike fossil fuel systems, it can provide a degree of energy independence by allowing countries to maintain a reliable and reasonably priced electricity sector, even if there are big geopolitical events that might be disrupting fuel supply chains. So, an example of a country that has some degree of energy independence through its electricity generation with geothermal is Iceland. So, according to the International Energy Agency, geothermal accounts for about 32% of Iceland's electricity generation. So that's pretty cool. All right, so the second geopolitical consideration is that it's location dependent. So historically, geothermal power plants have been very geographically limited because there are not a lot of places across the globe where there is this natural geothermal resource where there are hot rocks, there is the naturally occurring underground water reservoir, and then the rocks deep underground are naturally permeable to allow that water to circulate through. So these geological requirements have restricted the build out of geothermal power plants to a relatively small amount of locations around the world. But this will not be the case for long. As I mentioned before, enhanced geothermal systems use drilling techniques or drilling and fracturing techniques to create these to break up the rock and create these permeable pathways through hot rock, which allow water to be injected down into the well, into these rocks, to then be harvested for a geothermal power plant. And this enhanced geothermal systems allow us to build out geothermal power plants where there isn't this natural hydrothermal system that naturally exists. Okay, and then geothermal capacity. Yes, that was the next thing I wanted to discuss. So here in this map provides a high-level view of geothermal capacity around the world. And the first thing you'll notice here is there's this red highlighted region that I have here. And this is called the Pacific Ring of Fire. And this is a region that surrounds much of the Pacific Ocean, where Earth's tectonic plates meet. And here you can see the Ring of Fire. It goes all along North America and South America, and it stretches across Eastern Asia and goes all the way to New Zealand. So it covers Indonesia, Philippines, Japan, etc. And so in many areas along the Ring of Fire, there is one tectonic plate that is forced beneath another. And this leads to magma formation relatively close to the surface of the crust in comparison to other areas around the world. So this means that there is more heat in this Pacific Ring of Fire. There's more heat that is located close to the surface of the Earth because of these tectonic plates. So most of the existing naturally occurring hydrothermal resources are located along these regions. So this is where most of geothermal power plants have been built out to date. But again, with enhanced geothermal system technologies, this will allow geothermal power plants to be built in other areas across the world. Now, a few other countries that, because of various other factors about their geography, also have geothermal capacity are Iceland, which I mentioned before, Italy, Turkey, and Kenya. So if you're interested in that, you can look into the geothermal resources in those countries as well. And then the last geopolitical consideration is the utilization of infrastructure and the workforce from the natural gas and oil industries. So enhanced geothermal systems, EGS systems, utilize similar fracking infrastructure to that used in the oil and natural gas industries. So this makes the build out of geothermal infrastructure a lot easier because there are minimal additional workforce skill requirements and minimal new infrastructure to build out because the geothermal industry can start using natural gas and oil infrastructure. And one of the big benefits of this is because the technologies used in the natural gas and oil industries has already hit what we call economies of scale. And the concept of economies of scale, if you haven't heard it before, is just when you produce a lot of something, it decreases the price of everything or every unit that you're generating. So for example, if you build out a giant factory and that factory builds bikes, I'll do my little sketch of a bike here. And if that factory builds out 10 bikes, well, you've had to build out all this infrastructure just to build 10 bikes. But if this factory builds 10,000 bikes, the cost of that factory is spread out across all those bikes. So therefore, each bike would be cheaper in the scenario where this factory builds out 10,000 bikes. And this is the concept of economies of scale. So because geothermal systems are pretty limited in how much they've been built out to date, but enhanced geothermal systems will allow geothermal technology to be built in many other regions. This normally would require developing a whole new supply chain of infrastructure to build out these plants. But because these EGS systems use the same technology as natural gas and crude oil fracking systems, this makes it actually a lot cheaper and easier to build out enhanced geothermal systems across the world using existing workforces and infrastructure from the fossil fuel industry. All right, that was a little wordy. But yeah, that is it for our geothermal lecture. Thank you so much for watching. This is the first version of our geothermal lecture, and we are aware there is much that can be improved in this lecture, so we would love your feedback. Do you think that something was not explained clearly enough? Do you think that there is other information that we should add into this video? If you have any thoughts, we will be adding a link for a feedback form. And then after receiving a sufficient amount of feedback, we will be updating the lecture, re-recording, and posting the updated video. So for those of you who provide feedback, thank you so much for helping to improve the quality of publicly available education. Also, if you found this lecture valuable, please consider donating to help us continue making publicly available educational content on the electricity industry. We will provide a link in the notes, but you can also donate through visiting our website at pearlstreetstudio.org. All right, that's it for this lecture. See you next time.